So while the nucleus of the atom was discovered in 1912 by Rutherford and Marsden and Geiger, the exact structure of the nucleus wasn't understood for at least 20 years after that. It was quickly noticed that the mass of nuclei was heavier than could be accounted for just by counting up the protons. It was understood that the hydrogen nucleus was just the proton, but that there must be something else happening in heavier atoms. And it was thought that maybe there were electrons bound in with the protons to count for it, so that an alpha particle would be 4 protons bound with 2 electrons. But that doesn't work because of the quantum mechanics. If you bind an electron in that small a space, it must have a very large momentum, a large de Broglie wavelength, which would be much bigger than the nucleus itself. So there had to be some neutral particle combining with the proton that came to be known as the neutron, even before it was discovered. So the story of the discovery of the neutron begins in the late 1920s, when the second generation of Curies noticed that alpha particles bombarding beryllium and boron as well produce a penetrating radiation that was as penetrating at least as gamma rays, but maybe even more so. So that in the diagram that I have here, you have a polonium source and you have some beryllium, and the alpha rays come in, and out comes some unknown radiation that's more penetrating than gamma rays. One notices the penetration by seeing how much lead material you would have to put in front of it to get rid of it. And it was more than would be needed by gamma rays, though not by that much. It was then noticed that if you, in addition, put in some paraffin wax, which paraffin is a petroleum byproduct, and so there are a lot of hydrogen atoms as part of that, that on this unknown radiation would produce protons on the other side, and those protons you could then measure in an ionization chamber. One could also then put lead in between the protons and the ionization chamber to see how far they penetrated, and because you know what protons are, you can, and by saying how much they're reduced by ranging out, you could detect that the maximum velocity they had was something of order 3 × 10 to the 9th centimeters per second. That's 1/10 the speed of light, so that's a pretty high velocity, and it turns out that's a kinetic energy for the protons of about 5 MeV. So the question then became, what was the unknown radiation between the alpha particles and the beryllium and the paraffin wax producing the protons? And so the two answers for that were, well, one, it could be a quantum of radiation. In the late 20s, quantum mechanics had just been produced, and the Compton effect, whereby electrons were scattered away by photons, had been produced. So in Compton scattering, a photon comes in, hits an electron at rest essentially in an atom, and then the photon scatters away, but it's at a lower energy, and the electron recoils with some. So if we imagine that instead this is a proton and some radiation comes in, the more energetic, now scattered proton could be what was happening. And so that was one topic. The problem is that you need, the way Compton scattering works, you need a 50 MeV photon coming in order to get, at max, a 5 MeV proton coming out. And it's hard to see how you can get 50 MeV photons from an 5 MeV alpha particle on the beryllium. It could come from various binding effects, but in fact it can't, because those are all limited to about 10 MeV. And so it's hard to see how you can get 50 MeV. Or one could have just simple kinematics, kind of like your Newtonian bouncing of rigid balls. You would have some particle coming in, hitting a proton at rest, giving all its momentum to the proton. So afterwards, the initial particle stops stops in its track and the proton goes in. Therefore, you only need a 5 MeV particle coming in to transfer all its momentum to a proton coming out if you assume they have about the same mass. An additional factor was that in addition to having paraffin wax with its hydrogen, you could put nitrogen, some kind of nitrogen material inside, in which case out comes not protons, but nitrogen nuclei. And because of the much heavier mass in that case, that was even harder to explain with the Compton effect. And you need even more energetic photons or radiation coming in, and that was hard to understand. So, in fact, the best explanation was that there was a neutral particle of the same mass as the proton, which was produced, and that particle was clearly then the neutron. So that was the discovery of the neutron in around 1932. And I'll include a paper that you can see that effect in the notes. So with the discovery of the neutron, most of nuclear phenomenology could now be understood in that all atomic nuclei were made up of neutrons and protons. Neutrons and protons have roughly the same weight, so that then you can just count the number of neutrons and protons. We usually use Z as the atomic number. That's the number of protons. It also goes with the chemical element because you need to have Z electrons to go with the Z protons to have an electrically neutral atom, and the number of electrons influences the properties of the element. Then you have N neutrons as well, and the sum of the number of neutrons and protons gives the atomic mass. That's the mass of the atom, but it's mostly the mass of the nucleus. And then you can plot all the elements and combinations of neutrons and protons on what's called a Segre plot, where you make boxes for the number of neutrons on this axis and the number of protons on this axis, and you can then label all the various types of nuclei there. For instance, the hydrogen nucleus is just a one proton that's here at 1, 0, on this axis. There's also the deuteron, which is still atomic hydrogen, has those properties of atomic hydrogen, but it's a neutron and a proton, one proton, one neutron together, still charge 1, so it's 1, 1 on this axis. You can add a proton to this to get helium-3, or you can add another proton and neutron to get helium, the more common helium, or alpha particle, which is 2 neutrons and 2 protons. So to talk about the various things, the various types of things we have here, of the atomic elements that have different number of neutrons but the same number of protons, we call all those things isotopes, and they'll be in one row of the Segre plot. So all the isotopes of hydrogen are along this line. There's 2 stable, 1 not quite as stable, and then some more things over here. And then you can have helium, which has 2 stable isotopes, helium-3 and helium-4. Lithium is along here. All the isotopes of that, there are 2 stable with 5 and 6 as the atomic numbers. Beryllium and so forth. Oxygen is up here on the top line of what I've shown here with 3 stable isotopes and a number of unstable isotopes. By the way, carbon 13 is this element here, which has 6 going up 6 rows, so 6 protons, but 7 neutrons to give carbon 13. It's not stable, and that's what's used as, and it decays, and that gives you aging effects. All the elements in one column are called isotones. They all have the same number of neutrons, and they have various nuclear properties that are similar. All the elements that weigh the same, all the nuclei that weigh the same, we call isobars. They form this northwest-southeast line along the Segre plot. And just to use this plot, I'll show the various kinds of things that one has in the radium decay chain that we talked about last time, and that was used in the discovery of the nucleus. So radium itself, the most common part is a alpha decay emitter. It's up here on the plot. It emits an alpha, and an alpha is 2 protons and 2 neutrons, and you're losing those. So you go down to and to the left to get to radon. And radon itself is also an alpha emitter. That's what the yellow squares are on this part of the plot. By the way, I should say this part of the plot is way up here. We were showing down here before. Radon is also an alpha emitter. It emits to polonium-218, which is also called radium A. Radium A is also an alpha emitter. It goes to lead-214, otherwise known as radium B. Radium B is not an alpha emitter, it's a beta emitter. And so when you emit a beta, you change a neutron into a proton, and that means that you have one less neutron and one more proton, so you go one to the left and one up in a beta decay. So lead-214 goes to bismuth-214. Don't change the mass in a beta decay. And that's radium C. That is also a beta decay. It goes very quickly, less than a millisecond, up to polonium-214, which is radium C prime, which is then an alpha emitter, and goes down to radium D. I should say, actually, that it's polonium-214 only has the half-life of a millisecond. So it goes through that quickly. That's why it gets the prime. Radium D undergoes beta twice to bismuth and then to polonium, and finally polonium decays to the stable lead-210 by alpha emission. So what Rutherford saw in his scattering experiment was the alpha that came from this decay. Now, while the neutron and proton are approximately the same mass, and that to first order all the nuclear masses can be found from just adding those up, there is a slight difference in the mass because of the energy involved in sticking the neutrons and protons together. So we need to spend a couple minutes talking about how to measure nuclear masses. And the way to do this is to use a mass spectrometer, as is shown here. So in a mass spectrometer, you take a gas of a given type, and you have it in some gas volume, and then you ionize it by sending in a beam of electrons, and some of those now positively charged ions will be accelerated between the anode and cathode of this chamber, and just like in a cathode ray tube now, but with the anode and cathode switched, you get a beam of accelerated ions, positively charged atomic ions, coming out through here, and then they pass through a region of electric field between two plates and magnetic field into or out of the picture, which selects off a given velocity of those particles, and only some of those will go through some tiny slit that you have here, and then those will then go into a region that's electric field free but still has the same magnetic field, and they'll bend in a circle depending on their rigidity, which depends on their mass. They'll have the same charge, but they have slightly different masses so that they will go in different circles. And by measuring the radius of the circle, by where they hit on the far wall here, you can measure their mass. And while this is not good enough to measure 1 part in 10 to the 6th of the nuclear mass, it's certainly good enough to measure 1 part in 10 to the 3, and you can measure the mass deficits of nuclei in this way. In particular, when you have the two B fields be the same, the mass of the positively charged ion that you get depends on its charge times the B field strength squared times the radius of the circle divided by the electric field you used to select the field. So the electric field is here, one of the B fields is there, so B over E here is the selection. It selects the velocity. The second B here gives the curvature, which has a radius r, and the more charge, the more curvature And so by setting the B field and the electric field and knowing what charge you have, you find out, and measuring the radius, you get the mass of the particle. And you can tell the various isotopes of a given elemental species apart in this way and measure, in fact, their mass. Okay, so let's be a little more particular about what the masses are that we measure. So if you measure the mass of if you do mass spectroscopy with hydrogen and you measure the main part of that, which is just a proton, you find that it has a mass in MeV units of 938.28 MeV, which in our unit of atomic mass units is actually 1.0073, 1.0073 atomic mass units. And you might wonder, why is it not 1? And we'll come back to that in a second. If you still measure hydrogen, you'll also notice that there is deuterium there. And by measuring its mass and subtracting off the mass of the proton, you'll find that the mass of the neutron left over it's a little heavier than the proton at 939.57 MeV, which is 1.0087 atomic mass units. Now, I'll point out that if you take the mass of the neutron and subtract off the mass of the proton, you get something like 1.3 MeV, which is more than the mass of the electron. And so, in fact, the neutron is unstable and can decay into a proton and an electron, and as it turns out, a neutrino. And that's what beta decay is, though we haven't exactly talked about what the neutrino is yet. We'll talk about that well down the road when we start talking about particle physics. Now, the reason that the proton doesn't weigh exactly 1 U is because this unit U in atomic mass units of this sort is defined as exactly 1/12 the mass of the carbon-12 nucleus. So the mass of the carbon-12, it's actually the mass of the carbon-12 atom is 11.178 GeV and is exactly 12 U. And then we'll notice that if we take 6 times the mass of the proton and 6 times the mass of the neutron from up here, we find that's 11.267 GeV, and you'll notice that 11.267 minus 11.178 gives about 89 MeV left over. So that when you stick 6 protons and 6 neutrons together, you get something that is, in fact, 89 MeV lighter, and that excess energy, this 89 MeV, is the binding energy that holds that nucleus together. And so you can do this calculation for all the various isotopes you can think of. If you take the common stable ones and plot their mass, their binding energy, divided by the total A, in this case 12, but whatever it is for whatever element, you find that you get a curve that looks like this. So you get the average binding energy per nucleon. The carbon that we just were looking at is right up here. So it's like 7.5 times 12 is that total energy of 89 or something MeV per nucleus. So of course hydrogen by itself has no excess. Note that helium-4 here is very tightly bound, more tightly than you would expect, 7 MeV per nucleon. So, but then the other features that you can find are that, except for the lighter ones which go up, you come to a maximum, and it's in fact helium-56 that has the maximum binding energy per nucleus. It's the most tightly bound nucleus there is. And then as you continue on to higher and higher masses, you get slightly less binding energy. And that will eventually lead to the property that nuclei can spontaneously fission into smaller units that would be more tightly bound. Okay, so we know the mass of the nuclei. Let's now look at the nuclear size. And you can measure the size of a nucleus in the same way that Rutherford found the size of the nucleus, or that the nucleus was very small in his scattering experiments, except in this case we're going to use electrons because we need to accelerate whatever particle it is to very high energy so that it can actually hit the nucleus or go close enough to the nucleus that it will probe the real size of the nucleus. When you do that, you measure the difference in the scattering at each angle compared to what you would get from a point particle. So that, for instance, in these famous experiments of Hofstadter, and I'll have this experiment, this paper where I took this, he measured these in the around 1950. You can measure the cross section for going to a given angle divided by what you would expect for a point particle. And so, for instance, for carbon, he measured this cross section. Notice this is a log plot, and that on the x-axis we don't have theta, we have sine theta over 2, and it's scaled by a to the 1/3, the cube root of the number of nucleons. But in any case, you get this exponential-ish behavior falling off, and it's lowered so that we don't see all these lines piled up. Magnesium looks like this. Silicon, note, is right on here, and it starts, and it's a little less than 1, so there's less cross-section than you would expect from a point particle by a little bit, but then it goes much less, and then it has this little interference effect that you have much less than expected right here at around 2 on the x-axis, and then it goes up. Sulfur has the same spot when you've scaled by a cubed, as does calcium here, and even strontium here. So these all line up. They all basically say that you have a sphere of charge out to something, out to some fixed size, and then it stops. And that's what lines up all these things when you scale by that particular size. Later experiments were done, and I should point out that, of course, you have to make sure that it's elastic scattering of the electron. So the electron, you measure the same energy electron coming out as coming in, but it's at a different angle, so there is momentum transferred to it. And you need to adjust the energy for the various elements. So here you have 450 MeV electrons hitting nitrogen. You see that there is a series of these diffraction, and it's in fact just that. It's diffraction, like Fraunhofer diffraction of light on a hard disk. You get rings. These are the same rings seen in the electron scattering. Calcium has the same effect. Here now we're just looking at degrees, but if you fit the model, it fits very well to this constant charge density out to some radius for a sphere and then dropping off completely. When you take all those form factors and take the Fourier transform them to get the actual charge density, you get something that looks like this. So that for carbon and calcium and nickel and strontium and lead, you get all about the same density of charge out to some fixed distance, which grows as a to the 1/3 in Fermi here. So this is 6 Fermi. The proton turns out to be a little denser than that. I should note that in scattering electrons off of nuclei, you're really probing the charge density of the nucleus. But if you scatter protons in the same way, you can now measure the neutron distribution as well. The neutrons are not charged, but it does have a strong interacting, a nuclear interaction with the proton that you're scattering from, and it produces the same effects here where you have scattering with diffraction fringes. And so from both of these, one says that the nucleus has a constant density and a size. It's a sphere with a radius that grows as a to the 1/3 power.